Hello everyone. In this AV, we would be taking up the chapter Isothermal and Adiabatic Processes. We would study these two processes in details, look at the isothermal curve and the adiabatic curve. We will also calculate the work done in these processes, and finally we will derive a relation between Cp and Cv, which is the famous relation known as Mayer's relation. To start with, we will take up isothermal process. Now, as the name suggests, thermal word comes from temperature. So, when the system is undergoing a change and the condition is such that the temperature of the system remains constant, then such process would be known as isothermal process, because the temperature is kept constant and it's not changing. So for such processes, we need to have the system to be surrounded by a perfectly conducting material. Why conducting? So that whatever the heat is produced, let's say in the system, then it can be immediately given to the surrounding and the temperature remains constant. Or if any heat is absorbed by the system, then the same can be managed from the surrounding, and again we will have the temperature of the system to remain constant. Now, in nature or in general practice, we do not have any such material which is perfectly conducting. So, in general practice, a perfect isothermal process would be impossible. It can only be possible if the process takes place very slowly, so that the heat will find sufficient time to flow in or flow out depending upon the situation. So for an ideal gas, the isothermal process obeys something called Boyle's law for a constant temperature for a given mass of gas, and Boyle's law states that PV is equal to constant. Now, since the internal energy of an ideal gas depends only upon the temperature, and in isothermal process we do not have any change in temperature, so isothermal process will not produce any change in the internal energy of the ideal gas. Please remember this, because we will be using this when we derive the equation or relation called Mayer's relation, Cp minus Cv equal to R. Now, when we plot a graph between pressure and volume for isothermal curve, that graph will be known as isothermal curve. We are plotting pressure and volume for the isothermal process, and we plot the graph for two different temperatures where T2 is greater than T1. The second temperature is greater than the first temperature. So as we had discussed earlier, for isothermal change or for an isothermal process, the gas or the system obeys the Boyle's law, that is PV equal to constant. So we will find out the slope of this curve by simply differentiating the equation PV equal to constant. So PV is equal to constant. When we differentiate it, we will be using the product rule of differentiation. What does product rule of differentiation say? The product rule of differentiation, or simply the product rule, says that when we have to differentiate two functions which are the dot products, for example ddx of u dot v, so we assume one function to be the first function and the other one as the second function. So the formula says differentiation, first we write the first function, that is u, multiplied by the differentiation of the second function plus second function and differentiation of the first function. So it becomes ddx of u dot v is equal to u dot dv upon dx plus v dot du upon dx. The same formula will be applied for the equation PV equal to constant, but in this case we will be doing the partial differentiation. So the equation PV equal to constant becomes, we write the first function P dot differentiation of the second function or partial differentiation of the second function plus second function dot differentiation or partial differentiation of the first function equal to 0. Why 0? Because here in the main equation we had PV equal to constant, and please remember a constant can neither be differentiated nor be integrated. So since we cannot differentiate it, differentiation of a constant will give us 0. So we get the equation and we find out the value of dP upon dV. So I'll just show it to you. So we have the equation P dV plus V dP equal to 0. So we take it to the other side. So we take this term P dV to the other side and it becomes minus P dV. We have to get the value of dP upon dV. So dP remains as it is. We bring dV this side. It becomes dP upon dV is equal to minus P upon this V go this side. And we have dP upon dV as minus P upon V. So this is the equation which is also given here. We get dP upon dV for an isothermal change or isothermal process equal to minus P upon V. And this graph is known as isothermal curve. Now we go to the adiabatic process. As you know that adiabatic process is a process when a system is undergoing a change but no exchange of heat is allowed between the system and surrounding. Now for such a process to take place, we will be requiring the system to be perfectly insulated from the surrounding so that neither heat can escape nor heat be allowed to enter the system from the surrounding. Like in the previous case, that is for isothermal, we needed a conducting material. In this case, for adiabatic process, we will be needing an insulated material. But again, no material is perfectly insulating. So the perfect adiabatic process will again be impossible. But when a process takes place very fast or very rapidly, such that the heat doesn't find time to flow in or flow out from the system, then that process is considered as adiabatic process. Now for an ideal gas, an adiabatic process would obey the Poisson's law, that is PV to the power gamma equal to constant. Now this gamma is the ratio of these two specific gases, that is gamma is equal to Cp upon Cv. What is Cp? Cp is the molar specific heat at constant pressure and Cv is the molar specific heat at constant volume. What is molar specific heat? If the molar specific heat, amount of heat required to raise the temperature of 1 gram of a gas by 1 degree at a constant pressure, or when the pressure is kept constant, then that would be specific heat at constant pressure. But instead of 1 gram of gas, if we consider 1 mole of gas, that is the heat required to raise the temperature of 1 mole of a gas by 1 degree, then it would be molar specific heat keeping the pressure constant. So that is the term Cp. And for Cv, Cv is the molar specific heat at constant volume. How do we define molar specific heat at constant volume? It is the amount of heat required to raise the temperature of 1 mole of a gas by 1 degree, keeping the volume constant. Now if instead of 1 mole of gas we consider 1 gram of gas, then it will be simply specific heat at constant volume. Now specific heat at constant volume or specific heat at constant pressure would be denoted as small c by V, small c subscript V and small c subscript P. But when we consider molar specific heat at constant pressure, it would be capital C and subscript P, and molar specific heat at constant volume would be capital C subscript V. Now this equation PV to the power gamma equal to constant can also be expressed in terms of temperature and volume or temperature and pressure. What we have to do is we just have to consider the equation for ideal gas, that is PV equal to RT. Now from this equation we can find the value of P, which will be RT by V, and we substitute this in this equation. So instead of P we are writing RT by V multiplied by V to the power gamma equal to constant, and after calculation this will give T V to the power gamma minus 1 equal to constant. This one I'll just show it to you. So here we take the ideal gas equation PV equal to RT. From here we have calculated the value of P. V is taken to the other side, so we have P is equal to RT upon V. Now our main equation is PV to the power gamma equal to constant. Now here we substitute the value of P, that is R T to the power V and then V to the power gamma equal to a constant. Now this can be written as R T V to the power gamma minus 1, this going up, equal to a constant. Now this capital R is the universal gas constant. So if I take this R on the other side, constant by a constant will be another constant. That is why we can write T V to the power gamma minus 1 equal to a constant. This is what is given here, T V to the power gamma minus 1 equal to constant. Now in this equation, in this case we have substituted the value of P. Now we will substitute the value of V from this equation, PV equal to RT. So V will be RT by P, and in this equation we have substituted the value of V and we get this, T to the power gamma divided by P to the power gamma minus 1 equal to constant. Now if we plot a graph between pressure and volume for a given mass of a gas undergoing adiabatic change, then this is known as, the graph is known as Adiabatic curve. And to determine this slope of this curve, we have to differentiate this equation PV to the power gamma equal to constant. For this differentiation we would again be using the product rule, which is ddx of u dot v. So we assume this to be the first function and this to be the second function. First function differentiation of second function plus second function and differentiation of first function. And the basic rule of differentiation says whenever we have to differentiate ddx of x to the power n, the differentiation formula is n x to the power n minus 1. So using these two we will be trying to understand how they have got this equation. So our main equation is PV to the power gamma is equal to constant. So we assume this to be the first function and this to be the second function. So product rule says first function differentiation of second function. Here we are using partial differentiation. So we write V to the power gamma differentiation of P or del P. We call it del P plus second function and differentiation of this. So this is of the form x to the power n, and the formula says n x to the power n minus 1. But you have to notice one thing. Here the variable was x and we were differentiating it with respect to x. But in this case we do not have the same variable to which we are differentiating it. So another added term comes up, dv equal to 0, because a constant can neither be differentiated nor be integrated, and if we differentiate or integrate a constant we get 0. Now again we have to get the value dp upon dv. So we take all this term to the other side and we have v to the power gamma dp is equal to minus p gamma v to the power gamma minus 1 dv. Since we want to calculate dp upon dv, so this dv is brought on the left hand side and this v to the power gamma goes to the other side, and we have the equation dp upon dv is equal to minus gamma, this gamma we are writing before, p v to the power gamma minus 1 divided by v to the power gamma. Now this can be simplified using the basic formula x to the power m divided by x to the power n is nothing but x to the power m minus n. So if we use that, gamma and gamma will cancel out, we will be left only with minus 1, v to the power minus 1. So v will come in the denominator, and that is how we get dp upon dv is equal to minus gamma p upon v. So this is the slope of adiabatic curve and it is negative. So we know that the value of theta is obtuse. Now we will compare the slope of the isothermal curve and the slope of the adiabatic curve. The slope of the isothermal curve, if you remember, is minus p upon v, and the slope of adiabatic curve is minus gamma p upon v. So when we take the ratio for adiabatic, slope of the adiabatic curve to the isothermal curve, minus and p by v cancels out, we are left with gamma. So we arrive to the conclusion that slope of the adiabatic curve upon the slope of the isothermal curve is equal to gamma. What is gamma? It is the ratio between the two specific heat, that is gamma is equal to Cp upon Cv, the specific heat at constant pressure and specific heat at constant volume. So for this ratio we have to remember that the value of gamma will always be greater than 1, and the adiabatic curve, if you look at these two graphs, this is the graph for expansion and this is the graph for compression, because the volume is reducing here, and here it's expansion because the volume is increasing. So the adiabatic curve at any point has a steeper slope than the isothermal curve at that point. So adiabatic curve is steeper in this case, and in this case also the adiabatic curve is more steep compared to isothermal curve. Now in expansion, when we talk about expansion, this is the graph we are referring to. The adiabatic curve is below the isothermal curve and it is more steep than the isothermal curve, and in compression of the gas the adiabatic curve is above the isothermal curve, and here also we find that the adiabatic curve is more steep than isothermal curve. Now we try to find the expression for the work done by an ideal gas in isothermal expansion. So we assume that isothermal expansion takes place in an ideal gas. So the work will be done by the gas, and we assume that there are mu moles of the ideal gas. This is the symbol for mu, and the absolute constant temperature is capital T, and the gas expands from initial volume V1 to final volume V2. So work done is given as integration from V1 to V2 P dot dV. P is the pressure and dV is the small increase in the volume. Now we assume the ideal gas equation PV equal to mu RT, and we substitute the value of P from this ideal gas equation in this equation for the work done by the gas. So from here, PV equal to mu RT, the value of P will be mu RT by V. So this equation becomes W is equal to integration V1 to V2 mu RT by V dV. Now we have to understand that mu is a constant because it is the number of moles of the ideal gas that we have taken. So that will not change. So mu is a constant and it cannot be integrated. So it will go out of integration. Then R is the universal gas constant. Again, this is a constant, so this cannot be integrated and it will be out of integration sign. And T is the absolute temperature, which is also a constant because this whole process is isothermal, meaning the temperature will remain constant throughout. So mu RT, all these three terms are constant, so they are out of the integration sign. They cannot be integrated. So the equation looks like W equal to mu RT integration from V1 to V2 dV by V. Now dV by V, we have the integration formula. Integration 1 by x dx, or this can also be written as 1 into dx. So dx, integration of dx by x as log x. This is the formula. This is what they have used here. So integration V1 to V2 dV by V, the formula is log V, and then we have the limits. So this one is calculated as, this is the equation, W is equal to mu RT integration from V1 to V2 dV by V. So as we have seen here, the integration formula is integration of dx upon x is log x. So integration of dV upon V will be log V. So we use this formula here and our equation will look something like mu RT log V, and then we have the limits V1 to V2. How do we substitute the limit? In the previous AV also we have talked about it. That is, first we substitute the value of upper limit. This is the upper limit and this is the lower limit. So first we substitute the value of upper limit, and then minus the value of lower limit. So the equation becomes W is equal to mu RT log V2 minus log V1. Now log A minus log B can be written as mu RT log V2 by V1. So this is what they have got in the textbook. So they have mu RT log E V2 upon V1. Now from Boyle's law, what they are saying is the pressure multiplied by volume for the first gas is equal to the pressure and volume multiplied for the second gas. So from here we can find out the ratio of pressure and volume. So we find that V2 upon V1 is equal to P1 upon P2. This is coming from here. So P2 we have taken this side and V1 we have taken to the other side. So P1 upon P2 is equal to V2 upon V1. This is what they are writing. So instead of V2 upon V1, we can also write P1 upon P2. So this equation takes this form. Or we can say that W equal to mu RT log E V2 upon V1 or mu RT log P1 upon P2. Now this log base E when converted to log base 10 will be multiplied by 2.3026. So this equation takes the form W equal to 2.3026 mu RT log 10 V2 upon V1 is equal to 2.3026 mu RT log 10 P1 upon P2. Now here, as the gas expands, when the volume V2 is greater than V1, so the work done will be positive, which means the work is done by the gas. But if the gas is compressed, so V1 will be greater than V2. In that case, the work done is negative, which will mean that the work is done on the gas. Now we try to understand the work done by an ideal gas in adiabatic expansion. So for the work done by an ideal gas in adiabatic expansion, we again consider mu moles of the ideal gas and we allow it to expand adiabatically. So it goes from initial volume V1 to final volume V2. Then the work done by the gas is given as W equal to integration from V1 to V2 P dV, same like the previous case. But since this process is adiabatic, that means the expansion is adiabatic, so here we will not be taking the ideal gas equation. We will be taking the Poisson's law, that is PV to the power gamma equal to a constant, and that constant we assume it to be K. So from here, this equation W equal to integration from V1 to V2 P dV, we will substitute the value of P from this equation. So P will be K by V to the power gamma. So that V to the power gamma can be written as K V to the power minus gamma. So that equation takes the form integration from V1 to V2 K V to the power minus gamma dV. Now this integration we will understand now. So the formula for integration says integration of x to the power n dx is equal to x to the power n plus 1 divided by n plus 1 plus c, that is the constant of integration. So when we are deriving, for derivation purposes we ignore this term. So we will assume integration of x to the power n dx equal to x to the power n plus 1 divided by n plus 1. So here for this integration, for this equation, W or work done is equal to integration from V1 to V2 K V to the power minus gamma dV. So this is of the form this equation. Here K is a constant, so constant can neither be integrated nor be differentiated, so it will come out of the integration side, and then we will have integration K integration V to the power minus gamma dV, which will be of this form, and we will be using this formula. So K is a constant, comes out of the integration, and we have integration V1 to V2, integration from V1 to V2 V to the power minus gamma dV. We will use this formula, x to the power n dx is equal to x to the power n plus 1 divided by n plus 1. So here we will get V to the power n plus 1 by n plus 1 from the limits V1 to V2. Now this we can write it as 1 minus gamma, because 1 is with plus and gamma is with minus. So we can reshuffle the terms and we will have W is equal to K. Instead of gamma minus gamma plus 1, we are writing 1 minus gamma, both in the power as well as the denominator. Now this can be taken out, 1 minus gamma. So the equation looks like K upon 1 minus gamma, and we have V to the power 1 minus gamma, integration limits from V1 to V2. Now we will simply substitute the limits. After we substitute the limits, what we get is this term. So this is how they have got k to the power 1 minus gamma, k by 1 minus gamma, and v to the power 1 minus gamma, integration limits from v1 to v2. So when we substitute the limits, first we substitute the upper limit minus the lower limit. So we have k 1 minus gamma. In this term, first we have substituted the upper limit. So v becomes v2 1 minus gamma minus the lower limit, that is v1 1 minus gamma. Now k is multiplied inside, and what they have done here is they have taken minus common. So once they take minus common from here it was 1 minus gamma, now it becomes gamma minus 1. That minus will be here. I'll show it to you in a piece of paper. So we have the term W equal to K W equal to K 1 minus gamma, V2 1 minus gamma minus V1 to the power 1 minus gamma. Now we have taken minus common from here. If we take minus common from here, we keep the minus, and this becomes plus and this becomes minus. So we alter the terms. So we have K gamma minus 1, and this whole thing remains as it is. Now this minus is multiplied inside, so this will become minus V2 and this will become plus V1. So we alter the terms here. Plus V1 is written first, minus V2 1 minus gamma. Now what we do is, this term remains as it is. Here we have multiplied this k inside, so it becomes k V1 to the power 1 minus gamma, this minus k V2 gamma or 1 minus gamma. Now we have multiplied the k inside, and what we have done is, it was 1 minus gamma, so we have taken minus common. Minus, if we take common, this gamma becomes positive and this 1 becomes negative. So we alter the terms again. Taking minus common, it becomes gamma minus 1. Here also we take minus common, so it becomes gamma minus 1. Now anything to the power minus something, so this whole thing can be written in denominator to remove the minus. So it becomes W equal to 1 by gamma minus 1 bracket K by V1 gamma minus 1 minus K by V2 gamma minus 1, so that we can remove this minus. So this whole term has been shifted to denominator. This is what is given in the book as this equation. Now again what we do is, here the Poisson's ratio is PV equal to K. Now we have two pressures and two volumes, so we write P1 V1 to the power gamma is equal to P2 V2 to the power gamma equal to that constant K. And here in the previous equation we had K, so we substitute the value of K from this equation. So first we substitute here P1 V1 to the power gamma, and here since this is V2, so we substitute P2 V2 to the power gamma. Now 1 by gamma minus 1 remains as it is. Here P1 remains as it is. V1 to the power gamma divided by V1 to the power gamma minus 1. This is of the form x to the power n divided by x to the power n. So it will be x to the power m minus n. So gamma minus gamma plus 1. So gamma will cancel out, and we will have V1 to the power plus 1, that is V1 only. Similarly here also, so we have W equal to, or work done equal to 1 by gamma minus 1 within bracket P1 V1 minus P2 V2. So this formula is for the work done, and here you will see that we had taken mu moles of gas, but that term is not contained in this final formula. Now this can be modified in terms of temperature. again using that PV equal to mu RT. So P1 V1 will be equal to mu R T1 and P2 V2 will be equal to mu R T2. So instead of PV1 we will be substituting mu R T1, and instead of PV2 we will be substituting mu R T2. Now mu R is common, so we will take it outside the bracket and we will have T1 minus T2. So if we consider it for 1 mole of gas, then mu will be 1, the value of mu will be 1, so mu will disappear, and W or work done will be given as R upon gamma minus 1 T1 minus T2. Now this equation tells us that the work done depends only upon the initial and final temperature, that is T1 and T2. If the work is done by the gas for adiabatic expansion, so work done or W will be positive. That means the gas is cooled. And if the work is done on the gas is heated up. Now to compare the work done in isothermal and adiabatic process using this graph. So here this is for the expansion and this is the adiabatic curve, this is the isothermal curve. Now if we want to find out the work done, then we know that work done is given as the area under the graph. So here it is clear that for expansion, work done for isothermal process is more than the work done for adiabatic process. For adiabatic process, the area will be this much, and for isothermal it will be from isothermal curve up to the x-axis. So obviously isothermal curve has got more or bigger area, so work done for isothermal curve is more. When we talk about compression, so this is the graph. For compression, isothermal has got a lesser area, whereas adiabatic has got more area. So in case of compression, the adiabatic curve lies above the isothermal curve. So for compression, work done in adiabatic curve is more than the isothermal process. Now you can go through the difference between isothermal and adiabatic process, which we have already discussed. Here in the book they have given it in table form. Now we go to the Mayer's relation, that is relation between molar specific heat Cp, that is at constant pressure, and molar specific heat at constant volume, that is Cv. So the definitions are given here, which we have discussed earlier while discussing these curves or while trying to define this ratio gamma. Now for this we will be using the first law of thermodynamics to prove the Mayer's relation. So here for this proof, that is Cp minus Cv equal to R, which is also known as the Mayer's relation, we consider 1 mole of an ideal gas having pressure P, volume V and absolute temperature T. We also assume that Cv and Cp are the molar specific heat at constant volume and at constant pressure. Now we will heat the gas first at constant volume and then at constant pressure to establish a relation between the molar specific heat at constant volume and molar specific heat at constant pressure. So when the gas be heated at constant volume, the temperature is raised, and we assume that it is raised by a very small amount, that is dT. So to calculate the heat supplied would be molar specific heat multiplied by the increase in temperature. So molar specific heat at constant volume is Cv multiplied by the increase in temperature. So it becomes Cv dt. Now as the volume remains constant, the work done will be 0. There is no work done. Now we have the first law of thermodynamics, dq equal to du plus dw. dq is the heat supplied, du is the increase in internal energy, and dw is the work done. But here the work done is 0. So this term dw will be 0, and this is the heat supplied dq. So we have already seen that the heat supplied is Cv dt. So here dq we will substitute Cv dt, du remains as it is, and dw is 0 because there is no external work done. So we have Cv dt equal to du. We assume it to be equation 1. Now we heat the same gas at constant pressure. In this case we had heated it at constant volume. Now we are heating it with constant pressure. So at constant pressure again there is a rise in temperature, and we assume it to be dt only. Now the heat supplied in this case will be specific heat multiplied by the increase in temperature. So specific heat in this case is Cp because we are heating it at a constant pressure, multiplied by the increase in temperature dt. So the gas would expand. Now this expansion is the work done against the applied pressure P. So there will be a change in volume. So we assume that dV is the change in volume. Gas had expand, so the volume will increase. So we assume that dV is the increase in the volume or change in the volume. So work done is pressure multiplied by volume. So work done is pressure multiplied by volume. Now here again we take this equation dq equal to du plus dw. So when we heat it at constant pressure, dq is Cp dt and dw is Pdv. So this equation, the first law of thermodynamics, dq, instead of dq we are writing Cp dt is equal to du. So du remains as it is, and in place of dw we are writing Pdv. Now the temperature change is same in both the process, at constant volume and at constant pressure. So it remains same, but the internal energy will depend on the temperature. So in the previous case and in this case, the change in internal energy is du, and it is same for both. So we will transform this equation in terms of du so that we can equate these two. Now if we consider this in terms of du, then it would be we have this equation Cp dt is equal to du plus Pdv. So with this, du would be du equal to Cp dt minus Pdv. Pdv goes that side, so it becomes minus Pdv. Now this becomes our equation 2, and then we had equation 1. This was our equation 1, du equal to Cv dt. Now both these equations are in terms of du. So we equate these two, and we have this Cp dt minus Pdv, that is equation 2, is equal to equation 1 Cv dt. Now we bring this term this side because this also contains dt and this also contains dt. So we will have Cp dt minus Cv dt, this coming this side becomes minus, and this minus Pdv going that side becomes plus Pdv. Now here we can take dt common, so we will have Cp minus Cv, and dt we have taken common is equal to Pdv. Now we will leave it here, and we know that the ideal gas equation for 1 mole of a gas is Pv equal to RT. Now we partially differentiate it at constant pressure. So if the gas is allowed to expand at constant pressure, that means pressure is a constant, R is universal gas constant. So when we partially differentiate it, we will have P dV is equal to R dt. P dV equal to R dt. Now going back to equation 3, here on the right hand side we have P dV. But from this equation we know that P dV is equal to R dt. So here in equation 3, instead of P dV we will substitute R dt. So the equation will become, so this equation Cp minus Cv dt is equal to P dV becomes Cp minus Cv dt equal to R dt, because P dV equal to R dt. Now dt dt cancel out and we have the equation as Cp minus Cv equal to R. This is the famous Maier's relation, or relation between molar specific heats. This is the molar specific heat at constant pressure. This is the molar specific heat at constant volume. So Cp minus Cv equal to R, which is also known as Maier's relation. Thank you.